For the last 20 years, I've been doing research on a friggin' endodontic file, no more than 1 millimeter in diameter and 16 millimeters in length. Someone once asked me, why didn't I just do 1 millimeter per year and save 4 years? But sometimes just a little bit will make a tremendous difference. Just ask this guy. He lost $1 million with less than 16 millimeters. With just a little bit more information provided by research, you can accomplish more, much more, than can be illustrated in the exhibit hall with any file and any technique. Using no lubrication, no hand files, no cleaning of the flutes, no extrusion through the apex, and with coronal bioemulation, and no wasted time or treatment compromise. Little bits of validated information can make major differences. Do you know what your file looks like? Can you compare the performance of your file with the other files? These are bits of information that you need to know. My objective in doing research is to provide that information. Imagine for a minute that you can save 1 minute for every case as an endodontist, and that you do 6 cases a day. That's 1 hour a day. And if you work 200 days a year, that's 200 hours. That's 5 weeks of time you either saved or wasted. I think we can have a better foundation for understanding if we start with just when files evolved, how they evolved. In 1938, Dr. Maynard invented the first endodontic file. He took a watch spring, spread it apart to the shape of a cone, and ground the outside surfaces to make the first file. Our first commercial file, however, started in 1900. It was the K-type file, and that extends to today. We are not very rich in the advances that's taken place from 1900 until today. Somewhere along the way from 1900 until today, however, 2 occurrences developed. One was the advent of nickel titanium. Nickel titanium was not very strong as far as stainless steel was concerned, but it was much more flexible. And it offered a opportunity to increase the strain on the instrument without increasing the stress. As long as we stayed within those parameters, we could use rotary instrumentation. However, we needed to compromise that lack of strength, and we devised a way to minimize the amount of stress by using graduating tapers. By using a file that has the same taper as the canal, you're maximizing the stress on the instrument. By using different tapers, however, you can minimize that stress. If you use an instrument that is larger, has a larger taper than the canal, it initially only engages in the coronal aspect. If, on the other hand, you use a file that has a taper that's smaller than the canal, then it only engages in the apical portion initially. You may remember the old Maximum series that I introduced in 1993. It utilized 3 different file designs and 6 different tapers. When we got up to size 25 using an 02 taper, then it went to an 03, 04, 045, 05, and 055. And if that didn't work, then you recapitulated on the cycle. But let's get back to the 5 parent designs, the basic designs that we use. We use only these 5 files, are the derivations of these files. with every file we use today. We start with the K-type file, which was introduced in 1900. It had a 45-degree angle on its cutting edge, so it was mostly a scraping angle, and it was not very good for rotation, so it was used as a file, a push and pull motion. 4 years later, we introduced the K-type reamer. It's called reamer, of course, because the mode of operation was primarily rotation. That's the most popular design used today for the files that we have. It had a 60-degree angle, therefore being more adaptive to rotary instrumentation, and the files that we use today encompass the vortex, the twisted file, high flex, brace, and others. It wasn't until 40 years later that the headstrom file was introduced. It wasn't very good for rotary instrumentation because the cross-sectional area was too small. So in 1965, the gyro file was introduced. It was a three-fluted headstrom, or H-type instrument we call, that was used in a reciprocating handpiece. Today, that design encompasses the Hero, the Edge, and the Endo file. They all have slightly more than a 60-degree angle of incidence, or a rake angle, as we call it, cutting angle, but not much more, and it actually had less area for debris accumulation in the flutes than the triangular file. The next file to come along was introduced by me. The Unifile was designed by Derek Keith, and I designed the Dynatrack. The Unifile was a hand file. The Dynatrack was used in a reciprocating file. And that was done in 1978, having slightly more of a cutting angle than the triangle, but not much, but a great deal more area for debris removal. The files used today utilizing that design is the M2, the F360, and the Recipro files. These four files were introduced before nickel titanium. The file introduced after nickel titanium was the Quantec and K3 file, which I invented and introduced in 1996. The unique thing about the Quantec was that the three cutting edges were asymmetrical in placement. They were placed with unequal distances, which had a great deal of potential as far as the design was concerned, but it didn't change from introduction until today. The manufacturer was unwilling to maximize that design. Other than these 5 designs, then we have the modifications. We go to the triangle first, and the first modification was the U file, again introduced by Derek Heath. It compensated for the lack of strength by adding additional cross-sectional area beyond which the triangle had. It also had lands, which was thought to help in avoiding the transportation and curvatures. The downside of the lands was it caused abrasion against the wall of the canal, but it still had a 60-degree angle of incidence, or cutting angle, which was good. The next modification was the Pro Taper series, again having more cross-sectional area than the triangle, but it compromised some as far as the cutting angle was concerned, ended up with more of a scraping angle. The modification of the Pro Taper series was the Wave 1, which reduced the cross-sectional area, made it slightly more flexible, but it brought the cutting angle back to 60 degrees. But you see, it also rotated in a counterclockwise direction and was used in a reciprocating manner, but required a handpiece. It was another way for the manufacturers to get a little deeper in your pocket, because now you had to have a special handpiece to use the file. One thing that hadn't been addressed as far as file design was concerned was that the torsional stress on the instrument caused by the debris in the flutes of the file could account for as much as 50% of the torsion that the file encountered. So we reduced the cross-sectional area of the file, and the way that was done was just removing one side of the square to end up with a rectangle, but just removing one side. You had less cross-sectional area, so it was more flexible. It provided more area for debris removal, but it went back to the 1904 scraping action, the 45-degree cutting angle, more of a scraping angle, as a matter of fact, that the original file had. It compensated for that somewhat by having a center of mass that was different from the central axis of rotation. Therefore, the file moved back and forth slightly and provided more efficient cutting. Eccentric rotation. The problem, however, it was symmetrical from the tip to the handle, so you had that reduced cross-sectional area at the tip, making it more vulnerable to failure. You can see that in a torque-limiting handpiece, providing enough torque to rotate in the larger portion of the instrument was enough to break the tip of the instrument when it became engaged. The triangle utilized the same concept by removing one side of it to provide less cross-sectional area and more area for debris accumulation. This is a sequence ESX type file. It did provide less cross-sectional area, which made it more flexible. It increased the area for debris removal. It did get back to the 60-degree angle of incidence, or cutting angle, which made it more effective than the rectangle. Again, though, it also had a center of mass that was different from the central axis of rotation, which increased its efficiency as far as cutting was concerned. But it was symmetrical again from the tip to the handle, making the tip more vulnerable to failure. We took all of these different designs, the original 5 basic designs and all the modifications, and in search of designing an ideal file, we measured all the features and properties of the file. You may have gotten this, you should have gotten this in an email for all the different files. We took the manufacturer of the file, how many flutes it had, the size, the spirals per 16 millimeters, the helix angle, the cutting angle, the debris removing area, the rotation to failure, the peak torque at failure, the flexibility, if there was any plastic deformation, the file core area relative to the circumference area, the file core area relative to the file cross-sectional area. We looked at SEMs of the tip and any notations that we may have had during its performance in enlarging a canal. We did this for virtually every file, trying to find a common thread which would contribute to designing a more ideal file. Did we find any correlations? That common thread? No, we really didn't. Nothing we could hang our hat on. So it really didn't help much as far as designing an ideal file was concerned. We also looked at all the SEMs, the surfaces of the SEM, to see if that could provide some evidence as far as performance was concerned. Now, it did provide some evidence as far as the limitations were concerned, but those limitations were certainly within proper technique. We shouldn't have had a problem with the file as far as inherent faults were concerned as long as we were using proper technique. So were there any correlations there? Again, nothing we could hang our hat on. With all this research, I think you would agree that I would be a good candidate to be inducted into a museum, a very prestigious museum at MIT. That museum is called the American Museum for Useless Research. Wasn't entirely all useless, but it didn't help us find an ideal file. So where do we get our information to determine what file is better than another? How do we evaluate files? Well, we'd like to think that we turn to peer review literature, like we find in our journals, and we take each bit of research, which is usually confined to one area, like flexibility or resistance to torsional failure or whatever, and then we take the best of each one, add them together in hopes that we can extrapolate then to reach a conclusion about which file is better than another. That has its problems, however, because it all doesn't add up, particularly statistically speaking. I like to use the illustration that if you put this fellow's left foot in cold water with dry ice, he is excruciatingly uncomfortable and injury can result. If, on the other hand, we put his right foot in boiling water, again excruciatingly uncomfortable, and injury can result very quickly. However, statistically speaking, if we put his left foot in cold water and his right foot in boiling water, then he's very comfortable, which we know is not the case. But it's the same with files. It doesn't always add up, selecting one feature and another feature and adding them together to get what would be called an ideal file. If we take flexibility, for instance, and you isolate that from every other factor, how does it contribute? How do we determine what is the best imbalance as far as using flexibility and resistance to cyclic fatigue as far as other factors are concerned? Because when we take torque, the more resistance you have with cyclic fatigue is concerned, the less resistant to torsional failure you have. So what's the correct balance? Is it, if you're comparing one instrument to another as far as percentiles is concerned, comparing them one to another, would it be in the 70 percentile for resistance to cyclic fatigue and in the 30 percentile for resistance to torsional failure? Or would it be vice versa? 30% for fatigue and 70% for torque? Would it be, as some manufacturers suggest, be in the 100 percentile for fatigue and a very low percentile for resistant to torsional failure? We don't know until we test. But I'd like to point out that I think that it's in vogue to devote so much of our attention to cyclic fatigue. Who holds their file in one position in one curvature for 10 minutes or 5 minutes or even for 1 minute or even for 30 seconds? It's really what is adequate, particularly when you're compromising as far as its resistance to torsional failure is concerned. When you bring out a file from the canal and it's untwisted, that's from torsion, not fatigue. Our goal actually is not to have the one that's the most flexible or the most resistant to torsional failure. Our goal is to maximize efficiency and minimize stress. If I wanted the most flexible instrument or the one that's most resistant to cyclic fatigue, then I would have it heat treated, I'd have many spirals, and I would have deep flutes. On the other hand, if I wanted a file that was more resistant to torsional failure, Then I would have no heat treatment. I'd have few spirals, and I'd have shallow flutes, but it would be very stiff. So what is ideal? You can't tell by comparing one to the other. Investigating single features requires multiple explanations. You have to know the other factors involved, even when we examine something as simple as an x-ray, which almost every manufacturer file company does. They always present an x-ray touting the attributes of the file. Take this x-ray, for instance. I consider it to be very difficult. It's about 170-degree curvature, and the radius is very small. It would be very easy to tout the attributes of the file using this x-ray. But this x-ray was taken in 1939 by Dr. H.B. Johnson. He was using carbon steel files. So it certainly wasn't the file that made the difference. It was the skill of the operator. Even today, that would require skill, using the files that we have. But for him, the files had nothing to do with the good result that he had. H.B. Johnson was the one that introduced the term endodontics, or endodontic file. There are too many factors and too many variables that interact in multiple ways to extrapolate from a single feature or a single ideal feature. My question was, do we need to change our concept of evaluation? I wondered about that. So I went to Oak Ridge National Laboratories. Oak Ridge has the second fastest computer in the world. It was the fastest, and it'll be the fastest again in a couple of years. This computer occupies 3 acres of space. It costs over $1 million a year just to cool. It has a capability of 20 petaflops. 20 petaflops is 20 million billion calculations per second. I applied for a grant. The criteria that they use is, does it have universal appeal? And there's over 40,000 root canals performed every day. More than that all over the world. So yes, it did. I didn't get the grant because we did get the first phase, but it turned out that it was going to cost us over $100,000 just to program the computer. There's so many different variables, things like the speed of rotation, the speed of insertion, where the file is engaged in the canal. Is it engaged in a curvature? Is it compound curvature? What is the angle of the curvature? Etc., etc. Too many variables. Their suggestion was that we measure the actual performance of the files, and then we can examine the features of the files and determine what features cause the performance. Well, fortunately, I have been doing that for 20 years, measuring the performance of the files, simultaneously measuring the stresses all at one time. Actually, I spent $100,000 on the evaluation equipment. We could program in all the different variables: the speed of insertion, the depth of insertion, the speed of the handpiece, the total amount of insertion, etc. And we could record all the stresses done simultaneously. So we would know exactly when the stresses occurred, where they occurred in the canal, and the magnitude of the different stresses. By studying the results then, we could represent the findings graphically. And we've done that for hundreds of files, actually thousands. And we can compare the results. What did this research reveal about potential improvements? Well, a lot was pointed out about the technique, because when you dial in different parameters, you see the results very quickly. And I can point out in 4 sentences what is the most efficient technique and the technique with the fewest risk. One is advance the file in the canal with no more than 1 millimeter increments with insertion withdrawal motions. Even if it wants to pull in, don't allow it to go in more than 1 millimeter at a time. And you need to be able to make 1/2 of millimeters worth of progress with the same amount of pressure. If you can't make that progress, then you need to get out and change to another file. And when you change to another file, you also need to change to a different taper. The last, and you can even forget about this because the first 3 sentences allow you to avoid any problems with this, and that is not to engage any more than 6 millimeters of a file if it's engaged in a curvature. For instance, if you're allowed to go in more than 1 millimeter at a time, engage too much at one time, then the file is certainly liable to distort. That's from excessive stress. However, if I take that same file and I only use half of the engagement and I go in with a pecking motion 1/2 of a millimeter at a time, then I can use that same pre-stress instrument without any difficulty. The other is we don't really know how much we engage, but if we go into a canal, say like with 2506 to a certain depth, and then we follow it with a 2504 and carry it 2 millimeters deeper, how much are we engaging? Not 2 millimeters, but 7 millimeters of engagement. I don't like that much engagement. To minimize the stress on the instrument, that's something we should avoid. That brings us to today. And it became apparent during our research that the function of a file changes along its working length. So how do we accommodate that change in function? We selected 2 different files and we formed a hypothesis that changing the dimensional proportions along the working length can enhance the performance. By selecting those 2 files, the triangle and the S-shaped file, we started off with a triangle as far as the triangle is concerned and ended up with a trapezoid toward the handle. With the S-shaped file, we ended up symmetrically with the S shape and then became lopsided toward the handle. And this was the appearance of the files. We did accomplish these changes by using 2 dissimilar tapers, side by side, one different from another. We call the S-shaped file the NanoEndo file and the triangular cross-section file the NanoEndo file. By testing the hypothesis, we took the XO 2504, which changed from a triangle to a trapezoid, and we took the control, which was identical except it didn't have the change to a trapezoid, and compared the 2 as far as their performance was concerned. The new concept advantage was that there was a 52% reduction in the torsional stress and a 57% in the reduction in the force of advancement. I'm used to working with 5 and 10% as being significant numbers, but here we have 50 and 57% reductions in forces that contribute to the propensity for failure. That is very significant. So let's take a closer look at the XO file. It has one flute that's introduced that's different from another. That causes a reduction in the cross-sectional area and an increase in flexibility. 2 blades engage with the same forces as 3. It seems counterintuitive that when you do with one of the blades, you would end up with greater efficiency in cutting. But those 2 engage with the same force as the 3 blades. There's greater area for debris removal, and the tip retains the strength as the original triangle at the tip. If we take a closer look, you can see how the triangular tip transforms to the trapezoid as we go toward the handle. When we look at its rotation, it looks like the file moves from left to right. Actually, the central axis remains the same, but the force of cutting does go from one side of the file to the other, ending up in what we call a Kaman effect, and increasing the efficiency of the cutting ability of the file. Next, we took a different file to compare that also had a reduction in the cross-sectional area of the triangle, but it did it in a different way. The sequence, for instance, removed one side of the triangle, but it had more flexibility, more room for debris removal, and it had the eccentric rotation as well. But the difference in the concept made a big difference in the results. And the new concept advantage resulted in a 46% reduction in the torsional stress and a 92% reduction in the force. We also compared it with a triangular cross-section file that had greater flexibility due to being heat treated, like the Vortex Blue. I'm not going to wait until all of these go through the completion of the cycle. But there again, we had a 55% reduction of torsional stress and a 90% reduction in the force of advancement. If we look at it in comparison to the ProTaper Next, also which had a eccentric rotation, greater area for debris removal, you see the results were a 49% reduction in the torsional stress and 48% in the force, and the tip broke. Does the concept work with other files? Well, I told you we used it on the S-shaped file as well, and that's the NanoEndo file. It's symmetrical, again at the tip, becomes lopsided toward the handle. You can see that even though we are now cutting with one blade as you advance toward the handle, with that one blade you have a reduction in the cross-sectional area, which increases the flexibility. The one blade engages with the same force as the two blades. You have greater area of debris removal, and you also have the Kaman effect that we described before. And the tip retains its strength. We accomplish this by having two different tapers side by side of the flutes. For the 04, for instance, we have 0.25. For the 06, it's 0.3. For the 02, it's 0.015. The interesting thing is when we compare the 06 with an 03 taper versus 06 with an 04 taper, even though both tapers are what we call recessive and do not engage into the wall of the canal, there was a big difference. Even with 1 degree change in the dimensions of the file gave us a very big difference in the results. The 03 taper had the advantage of a 46% reduction in the torsional stress and 80% reduction in the force. So we went with the 03-06 taper. And when you compare that with the Edge, which is also a H-type instrument, but a 3-fluted H-type instrument, and compare the two, the new concept was a 63 or 65% reduction in the torsional stress, 89% in the reduction in the force, and the tip broke. ProTaper Next, even though they call the ProTaper Next X2 file being an 2506 taper, we really aren't comparing apples to apples and oranges to oranges when we're comparing the ProTaper series, because they change and they have graduated tapers. But that was the closest that we could come to it. And I'm not going to continue to read the differences in the force, but you see it's very significant, and the tip broke. If you compare the one endo file with the sequence 2504, again, very significant differences, and the tip distorted. If you compare it with the Vortex, not the Vortex Blue, but just the Vortex, we ended up with less of a difference than any other file. And why is that? Why would it be less of a difference than the more flexible Vortex Blue? Well, they're exactly the same instrument, but one is more flexible than the other. But when you have linear flexibility, such as bending, that is also accompanied with axial flexibility. And what happens is the file begins to flex axially, not to the point that there's permanent deformation in the instrument, but one that does affect the function of the file. So the function actually is better for the Vortex than it is Vortex Blue. We did these comparisons with virtually every file that's out there, not comparing features such as flexibility, but performance. And for all of the tests that we've conducted, the NanoEndo file and the NanoEndo files have had better performance than any other file, just by utilizing a new concept. So our hypothesis worked. Dissimilar tapers definitely enhance performance. And that's the NanoEndo file and the NanoEndo file. Are there considerations for use even though we ended up with better performance? Yes. A file has three functions. One is to form a chip, another is to dislodge a chip, and another is to convey that chip coronally. If these instruments perform better because of their efficiency. So that means you get the same results with less force. If you apply the same force as you did with less efficient files, then you might be forming a chip that's not as easily dislodged, and it causes undue or unnecessary torsional stress. There are no perfect endodontic files, but the NanoEndo file and the XO file are significantly closer. Now then, the nice thing about this concept is it can be applied to virtually any file design and end up with beneficial results. Now, where may we be going? I can talk about what I have been doing and what I expect to happen in the future. Some of these have been folly and some still offer potential as far as benefits are concerned. I was interested in mass producing files, so there's a metal called liquid metal. Liquid metal you can cast, which means you can produce bucketfuls at a time. The files that were good were actually better than nickel titanium. However, the technology was immature and we ended up with folds in the casting, which caused very vulnerable parts. So that part would break very easily and would be inconsistent as far as ending up with good results were concerned. Being interested in mass production, I also had the design of a notch file, which you could produce 100 or 200 files at a time by going over the shaft of the instrument with like a meat cutter and cut notches in all the files at the same time, rotate them slightly, and do the same thing again. These files worked out pretty good, but it was again a different mode of manufacturing, something I couldn't afford and something I couldn't get anyone interested in manufacturing. A different mode of manufacturing is the laser. You can cut a conventional triangular shaped cross-section file with the laser. I was interested in cutting a nickel titanium tube. The interesting thing is the waste of one tube provides the mirror image or another file simultaneously. The laser cuts very smoothly, better than the grinding wheel. And the advantage is it can cut 400 inches per minute, which means we can produce files much more rapidly. But there again, it's a different manufacturing process and a very difficult thing to get other people interested in. This was a concept that I thought was folly. This is a heat set instrument. I introduced this instrument or applied for a patent in 2008 This is what I call the waffle type instrument in 2 dimensions, putting the file between a male and female portion of a jig and heat sitting it. But I was more interested in a coil instrument. That instrument did not patent, but it is the same as the true shape file, except I was more interested in the coil because it again offered another mode or modality for removing the debris from the canal. Is it a new concept? Remember how we started? That was with what Dr. Maynard did in 1938. It took 178 years to come full cycle. It's the same concept. Now, is there an exciting future today? And the answer is yes. You've heard a lot about additive manufacturing or 3D printing. You take a design and you digitally slice it in different sections all the way up from the tip to the end. You can change the design in as little as every 7 microns. You feed that design into the computer then, and then by taking a micro dust of the material, you can actually weld one layer at a time. You can make your own alloy. You can put titanium in one hopper and nickel in the other and make your nickel titanium. You put it in a vacuum chamber and you spread it to a very, very thin layer, like I say, 7 microns at a time, and you build it up one layer at a time using a laser to weld in the different design with each digital slice from one end to the other. And you can stack those different designs to utilize all the space that you want to use in a 14-inch by 14-inch block. It may take as long as 4 days to do that, but then you take out this block and you put it in another vacuum chamber and you actually blow away all the unused dust so it can be used again. But in that block, you can produce 340,000 pieces. That's half of the year's production on a global basis for nickel titanium files. And every one of them can be a different size or a different design. And the design can be changed all along the path from the tip of the instrument toward the handle. And how much does that cost? And is it a technology that's available today? The answer is yes, you can do it today. And it looks like it would cost about $20,000. That is 4 cents per instrument. Is that a technology we can be excited about? The answer, in my way of thinking, is yes. So you as an endodontist, you are not interested in straight canals. But as canals become more and more complicated, then advancement in file design becomes more and more important. Now, why do I do this? It's a challenge to affect an advancement in design. It's not a spectator sport, so it also invites the input from all of the users, particularly as they accumulate more and more knowledge. I think the NanoEndo file and the NanoEndo file are definitely advantages in that regard. I invite you to visit me, whether it's on the internet or by my phone or by email, or you can visit NanoEndo.com, or you can visit me in person. I am very fortunate to have a wonderful yacht on the Tennessee River, and I'd be happy to take you on a cruise down the beautiful Tennessee River. I think you will find it a thrill. We can't accommodate more than 40 people at one time, but I thank you very much.